Welcome back to the deep dive. Today, we are taking on just a massive computational problem facing large language models. We're going to drill right down to the fundamental mathematical structures that are, well, holding them back. If you've ever wondered why LLM inference is so expensive or why even the fastest models still feel like they're generating text one laborious word at a time, you are hitting the core bottleneck we're exploring.
It's a structural limitation. I mean, it's baked right into the foundation of pretty much all current LLMs. They all rely on an autoregressive generation process that operates on discrete tokens. Just think of your vocabulary as this massive but finite dictionary.
Okay, and how much information does one entry in that dictionary actually carry?
Surprisingly little. It's almost shocking. If you use a common vocabulary size, say 32,000 entries, mathematically each token carries only about 15 to 18 bits of information. You're generating incredibly complex language, huge structures of meaning based on these tiny, tiny discrete steps.
That makes perfect sense. So if you want a phrase like the continuous autoregressive model to be generated, you just can't do it in one step. That specific combination of words just isn't going to be a single entry in your discrete vocabulary. You have to predict the, then continuous, then auto, and so on.
Exactly. This low information density per step is the fundamental limit on throughput. And if you try to get around it by making the vocabulary bigger, say by adding all possible four-token phrases, it just explodes exponentially. The whole softmax step becomes computationally infeasible.
So the problem is a fixed bandwidth. The solution we're unpacking today, it just fundamentally breaks that ceiling by moving from discrete space to continuous space. This is the continuous autoregressive language model, or CAL.
Call is a genuine paradigm shift. It moves from predicting the next discrete token to predicting the next continuous vector. The whole mission here is to radically increase the what they call the semantic bandwidth of each generative step. They do this by compressing a chunk of k tokens, in their case they use k equals 4, into a single high-density continuous vector.
And if you compress 4 tokens into one vector, you instantly reduce the sequence length by a factor of 4. I mean, that has to be the key to the massive efficiency gains thereafter.
It is. But shifting from, the countable discrete world of tokens to the infinite uncountable continuous space, well, it means you have to throw out the standard mathematical toolkit. Things like negative log likelihood loss, perplexity, all of it is gone. We are diving into a system built entirely on a novel, likelihood-free mathematical toolkit.
Okay, so let's start at the foundation. How do they even create these high-density vectors? This has to be the compression engine, the autoencoder.
Right. The autoencoder has two jobs. First, take k discrete tokens and compress them into a single continuous vector, we'll call it Z, and then, crucially, be able to reverse that process to decode Z back into the original K tokens with extremely high fidelity. They got over 99.9% accuracy on reconstruction.
And the beauty of this is that the capacity of these continuous vectors is just gracefully scalable. If you need more information, you just increase the vector's dimensionality, right?
Precisely. But here's where the first real mathematical challenge comes in. If you optimize that autoencoder only for perfect reconstruction, you learn what they call a brittle representation. Imagine you have a smooth map. With a brittle map, moving your finger just a tiny bit to the side could suddenly jump you to a completely different continent.
Ah, so a tiny error in that continuous vector Z would just lead to a totally nonsensical sequence of tokens when you decode it. That would make any kind of downstream prediction impossible. The model would have no stable, smooth space to work in.
That's it exactly. The continuous space needs to be mathematically smooth or robust. The fix is to apply some serious discipline through what's called variational regularization. So instead of a simple deterministic autoencoder, they shift to a variational autoencoder, or a VAE.
Okay, so walk us through that. How does sampling and probability smooth out this map?
Well, the encoder doesn't just output a single fixed vector Z. It outputs the parameters, the mean, mu, and the variance, sigma, of a diagonal Gaussian distribution. The latent vector Z that the decoder actually sees is sampled from that distribution. You're deliberately injecting a bit of noise into the system.
I see. So if the encoder is trained to reconstruct the tokens accurately, even when its input vector Z is being slightly jittered by that sampling process, it has to learn to find the right neighborhood on that map, not just a single brittle point.
You've got it. And the total loss function reflects this. It's the sum of the reconstruction loss, which demands fidelity plus a penalty term. That penalty is the KL divergence. And it basically forces the distribution the VAE learns to stay close to a standard normal prior. It keeps everything tamed and well-behaved.
But there's a famous failure mode with VAEs, right? Posterior collapse. What is that and how did they get around it?
Right, posterior collapse is a huge risk. It's when the decoder becomes so powerful that it learns to just ignore the information coming from the latent vector Z. It figures out it can reconstruct the input tokens just based on context, and so some dimensions of Z they collapse to noise. They become useless.
The system gets lazy.
Yeah, it's a form of statistical laziness. So to prevent that, they use a clever trick called KL clipping. This forces every single dimension of that latent vector to actively participate in the reconstruction. It sets a minimum penalty, which forces the encoded distribution to maintain some variance, guaranteeing a dense, structured, and active representation.
And the result is a robust 128-dimension vector that compresses 4 tokens. This high-density vector sequence, Z, is now finally ready for the generative part of the model.
The robust continuous space is complete. But now we have to face the next huge mathematical obstacle.
Yeah.
How do you actually predict in this new space?
Okay, so we have this sequence of robust vectors, Z. Now we need a model that can predict the next vector in the sequence. Why can't we just use the standard negative log likelihood loss? That's the bread and butter of every traditional LLM.
Because the generative space is, it's R to the power of L. It's an uncountable infinite set. Traditional LLMs work because they compute an explicit probability distribution over a finite vocabulary. They can list every possible outcome. When you try to do that in an infinite continuous space, computing that probability density becomes mathematically intractable. You just can't normalize over infinity.
So they needed an objective function that doesn't require knowing the underlying probability density. And they landed on the energy transformer architecture. Why was that specific choice so important?
Because of the core mission, efficiency. Many of the other options for continuous prediction, like diffusion models or flow matching, they all rely on iterative sampling. To generate one vector, you might need dozens, even hundreds of steps. If you use an iterative sampler, you've just reintroduced the exact inference bottleneck Cove was designed to eliminate. The energy transformer is a black box model, but it's designed for high-quality, non-iterative, single-step generation.
And the theoretical foundation for training this thing is based on something called strictly proper scoring rules.
Yes, and this is a really critical mathematical concept. A strictly proper scoring rule is just an objective function that guarantees the model is incentivized to report its true predictive distribution. The objective is only maximized when the model's prediction, P, exactly matches the true data distribution, Q. Negative log likelihood is one such rule. The energy score is another, and it's perfectly suited for continuous space.
So the core idea behind the energy score is that we can use distance, which is easy to compute, to measure alignment instead of probability density, which is intractable. What does it actually measure conceptually?
It measures the alignment between the model's predictive distribution and the ground truth observation. But it does it all based on sample distances. It has these two competing terms that balance each other out. The first term encourages diversity. It measures the expected distance between two different samples drawn from the model's own prediction. So if the model just collapses and predicts one single point, this distance goes to 0, which gives it a huge penalty.
Okay, so it actively punishes the model for being overconfident and just spitting out one answer. What does the second term do?
The second term encourages fidelity. It works to minimize the distance between the model's sample predictions and the actual ground truth vector. So by simultaneously pushing its own samples apart and pulling them all closer to the truth, the model is forced to learn the true, complex, often multimodal distribution of the data.
And since you can't calculate these expectations exactly over a continuous space, they use Monte Carlo estimation for the training loss. They mention something specific, drawing n equals 8 model samples, but m equals 100 target samples from the VAE.
Yeah, that's a really clever engineering trick to stabilize training. Because the VAE structure gives us a known Gaussian distribution for the target. Drawing a lot of samples from it is cheap. So drawing m equals 100 target samples drastically reduces the variance of the loss estimator without adding much computational cost. It just makes the whole training process stable and feasible.
We've established how to train calm without explicit likelihoods, but now there's the evaluation problem. Standard metrics like perplexity are totally dependent on likelihoods, so they're useless here. How do you measure performance?
Right. They needed a metric that was both model agnostic and, this is the key word, principled. And a principled metric, in this context, has to reward models that are not just accurate, but also correctly represent their own uncertainty. If a metric only rewards giving high probability to the correct answer, a model could just learn to be confidently wrong all the time.
So they turn to the Breyer score.
The Breyer score. It's a classic, very rigorous scoring rule. Its power comes from its decomposition. Minimizing the expected Breyer score is mathematically equivalent to minimizing the squared error between the model's prediction P and the true distribution Q. It's a really reliable measure of calibration.
But just like the energy score, the Breyer score normally requires knowing the full predictive distribution P of X, which LLM's black box sampler doesn't give them. So how do they estimate it without likelihoods?
This is where the mathematical elegance really shines. They figured out a way to construct an unbiased Monte Carlo estimator for the Breyer score using only two samples drawn from the model. Let's call them by 1 and by 2.
Two samples? That seems impossible. How can two samples give you enough information about the whole distribution?
They leverage indicator functions. So the Breyer score has a term that reflects the model's uncertainty, which is the sum of the squared probabilities. It turns out this is mathematically equivalent to the probability of collision, the chance that two independent draws from the distribution land on the exact same spot. So they estimate this collision probability with a simple indicator function. Does by 1 equal by 2? If they collide, the model is seen as more certain, which affects the score.
That is a very clever substitution. So probability squared is estimated by collision probability.
Exactly. And the accuracy term, P of Y, is estimated just as simply. Does LL1 equal the ground truth Y? By combining these two sample-based indicators, they get a full, rigorous evaluation score without ever calculating a single explicit probability density.
And they wrap this all up into a composite metric they call Breyer LM, averaging scores across different n-grams for robustness.
And the validation was absolutely critical. When they tested Breyer LM on standard transformer baselines, where they do have access to traditional metrics, Breyer LM showed a near-perfect monotonic alignment with cross-entropy loss. The Pearson correlation was negative -0.6. That confirms they built a sound, reliable replacement for perplexity in this new continuous domain.
Okay, let's get to the final mathematical hurdle, controlling generation. In a standard LLM, we use temperature sampling. You adjust a parameter, it rescales the logits before the softmax, and you control the quality versus diversity trade-off. If LLM uses a black box sampler and has no logits, how do you tune the output?
They had to develop a really rigorous, provably exact method based on rejection sampling. The intuition relies on probability exponentiation. If you want a target distribution that's proportional to your original distribution raised to the power of n, where n is an integer, you can get that. You just draw n samples and you accept them only if all n of them are identical.
That's a clean mathematical idea for integer temperatures. But for real-world tuning, you need arbitrary temperatures, T, usually between 0 and 1.
Correct. And for any arbitrary t between 0 and 1, they mathematically proved in their Theorem 1 that you can decompose the problem. They split 1 over t into its integer and fractional parts, and then run a two-stage rejection process. The second stage uses some really sophisticated math, sort of related to the Bernoulli factory, to simulate the biased coin flip needed for the fractional part. The result is an algorithm that exactly samples from the desired temperature scale distribution.
That sounds incredibly precise, but also potentially brittle in a different way. If the exact procedure needs thousands of trials to find one successful sequence, haven't you just reintroduced that inference bottleneck?
That is the risk, 100%. The analysis of the expected cost showed the algorithm is hugely sensitive to the temperature T. If you want a very low temperature for high-quality, low-diversity output, that integer part n gets really large. The chance of drawing identical samples just vanishes. The rejection rates become massive, and the whole thing becomes computationally impractical.
So the exact math creates a computational wall. How did they find a practical way around this for low-temperature sampling?
They introduced a really elegant approximation they call the batch approximation. Instead of demanding n identical samples in a row, they take one single large batch of n samples, where n is way bigger than n. Then they do a combinatorial search. They look at how many times a sample X appears in that batch and assign its weight based on the number of successful n ducals it appears in. It's a binomial coefficient calculation.
Ah, that must improve sample utilization dramatically, because samples that would have been thrown out immediately are now actually contributing to the search.
Absolutely. And the mathematical assurance comes from Theorem 3. While it's biased for any finite batch size n, the algorithm is asymptotically unbiased. As that batch size n goes to infinity, the output distribution converges to the true target distribution. And empirically, they found that just adjusting the batch size n in LLM gave them a nearly identical accuracy-diversity trade-off as tuning the temperature T in a standard transformer.
So we've navigated the four major mathematical challenges: creating the robust space, training with the energy score, evaluating with LLM, and controlling generation. The final question is simple. Did this massive shift in the toolkit actually deliver on the promise of efficiency?
It absolutely did. The complexity of the math paid off in raw compute savings. Let's look at the specifics. They compared CalMM, a 371 million parameter model with a semantic bandwidth of k equals 4, against a comparable traditional model, Transformer S, with 281 million parameters.
Okay, so CalNem is a bit larger structurally, but it's doing less than half the number of forward passes because of that k equals 4 compression.
Exactly, and that translated directly into huge computational wins. CalM achieved comparable performance while requiring 44% fewer training FLOPs and, critically for deployment, 34% fewer inference FLOPs. I mean, that is a game-changing efficiency gain rooted entirely in this paradigm shift.
And their central hypothesis that the semantic bandwidth k could be a powerful new lever for efficiency, was that actually validated?
It was decisive. When they started CalM with k equals 1, so no compression, it actually performed a bit worse than the discrete transformer, because continuous prediction is just a harder problem. But by increasing k to 2, and then especially to k equals 4, CalM's performance curve dramatically shot past the traditional transformer scaling curve. It proves that k is a powerful new dimension that researchers can now tune to optimize that performance compute trade-off.
This whole deep dive has really shown how the LLM world is no longer stuck in that token-by-token paradigm. Calm successfully migrated generation to a robust, high-density, continuous vector space using a whole new set of likelihood-free mathematical tools.
Yeah, the key takeaway is that they successfully introduced semantic bandwidth, k, as a whole new scaling axis. We've moved beyond just thinking about model size and data size.
Which leads us to our provocative thought for you, the listener. Since performance now depends not just on model size and data, but also on this new factor, semantic bandwidth k, the critical next step for researchers has to be establishing a unified set of new scaling laws.
They need to figure out how to mathematically predict the optimal chunk size k for any given compute budget and data set. The focus has officially shifted from answering how big should the model be to answering the much, much harder question: how dense can we possibly make the predictive step?
A shift from size to density. That is a fascinating place to leave it. Thank you for guiding us through that.
My pleasure.
We hope you've gained some real insight into the future of LLM efficiency. Until next time, keep exploring.